All right, howdy party people. We are doing chapter 8.1, defining and using sequences and series. We'll start off with sequences, we'll go on to series. You've probably seen a lot of this. This first section is to introduce some notation stuff. We're not going to look at the patterns. You might remember things like geometric and arithmetic are two specific types of sequences, and we'll just kind of do a general one. Now we'll also hit what series are, but a sequence is just generally a list, and generally we also call it an ordered list of numbers. Now they can be these patterns, or they can also be neither, but we also talk about these if they're finite, meaning has an end. So it's set to a certain specific number of terms, or infinite, goes on forever. These are the two things that we'll generally see happen with our sequences. So we talk about sequences, and there's some notation I'll just point out real quick. We usually use a sub n, but you can also see here f of n happens. This is kind of just like our output. So you might think of it as our y value associated. But then what is n? N is the term number, in case you forgot about that. So in a sequence, we could have a list of numbers. Let's choose color here, and I'll get right here. So if I had something like a list of simple numbers, and there happens to be a pattern with this one, this would be my terms. These would be my terms, and we'd say that these would be the end values. This would be the first term, second term, third, fourth, fifth. And each of these we'd also call A1, A2, A3, A4, A5, right? So at n equals 1, we have a sub 1 equals 1. So let's go ahead and look at this. Write the first 5 terms by the rules. These are the rules. The rules you can think of as equations. So the first term is when n equals 1. So we say a of 1, a of n, we'll put up here. So, oops, and then n here. So say what happens when we get 1? I'm going to make this into a little table. And that's how you can think about it if you were doing this. Now, if you know the pattern, it makes it really easy. 1, 2, 3, 4, 5. So what happens when I plug in 1 here? Well, I'd get 2 times 1 plus 5. So that's 7. Now, if I recognize the type of equation, I don't have to plug in every number. In this case, this is a linear function with a slope of 2. It's going to add 2 every single time. So I'm going to go ahead and just do that. I'm going to add 2 every single time. Now, I wrote it as a table. If we want to write it a little more like a sequence is generally written, we'll write it like that. And there's our first 5 terms. Once again, I might look at this and be like, hey, this is geometric. What I recognize about this is that if I want the first term, I could plug in 1, 3 to the 1 minus 1, negative 3 to the 1 minus 1, which would be negative 3 to the 0, which is 1. And I should put this in parentheses. There we go. Now, what I should recognize is that this is geometric or exponential. It's going to multiply by negative 3 each time. If I was uncertain, I would just continue to plug in n, 2, 3, 4, but I'm seeing this pattern, so I'm going to go ahead. I'm going to multiply by negative 3 every time. So this is going to alternate positive to negative each time. And there's my first 1, 2, 3, 4, 5 terms. Right? These would be my n, or we could call them A1 through 5. Well, this one's asking us to describe a pattern. All right. So there's different ways you can do this. We're a little bit more guess and check here. So I'm looking at these numbers, and I'm like, well, it's not an add or a multiply, but I'm noticing these are special numbers. These are all cubes. What we have here is we have negative 1 cubed, negative 2 cubed, negative 3 cubed, and so on, negative 4 cubed. Well, those correspond to my term numbers. So we're going to call this negative n cubed. In this case, it doesn't really matter if I put the negative on the outside or inside. It should be the same. All right, so here's our rule for the nth term. So we'll say a sub n equals this. And it wants the next term. I believe that'd be negative 125. So it does require us to know a little number pattern. Here's fraction of strategy. Think of an equation for the top. So this goes 2, 4, 6, 8. Well, that looks like it's just 2n on top. 2 times the term number. 4, 5, 6, 7. Well, that's increasing by 1, and it's starting at 4, so that starts a little bit more like this. If I tried n plus 3, that'd work out great, because now if I plug in 1, I get that. And so that's a nice way to check. It's a little bit more on intuitively guessing and checking, but the strategy on something like this would be write an equation for the top, 1 for the bottom. What would my next term be? Well, it would be 10 over 8. Now, they didn't simplify there, so I'm not going to simplify mine either. A grocer is stacking apples. Okay, I love apples. 7 layers. Okay. We're going to write a rule for the number of apples in each layer. So if it's a square pyramid, that means each layer is a square. And that should be the hint here, is that it's a square. The first layer has 1, the second has 4. I need square numbers, since I'm using like defined units each time. Get to do something kind of similar to what I did here. I'm just going to say this is n squared, because that would work for all the layers. It'd be 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. It'd be 5, right? So we go a of n equals that. Let's check that it asks us anything else. Nothing really. All right, plot the points. Okay, layer, number of apples. So we're going to have our layer, which is going to be like our n, and we're going to have number of apples. And these are square numbers, so we're going to have layers 1, 2, 3. Now this should look like a parabola. 5, 6, 7. And this, let's plop this up here. Let's go 1, 2, 3. And so I might not get all my numbers in here, so I'm going to scale this by 2s, I guess. Oops. Just went against my own guessing. 10, 12, 14, 16, just so I can get more layers in. So 1, 1 would be about here, 2, 4, 3, 9, 4, 16. Now these are not connected. Why aren't they connected? Because we don't have a half a layer. Now it looks kind of like a straight line. You know, I might need to, don't want to make sure people know what I'm talking about. I might label these points. So that takes us to, what is a series? Because I brought up this word. A series is going to be the sum of a sequence. So meaning we're going to change, if we had something like a sequence like this, it's very, very simple sequence, this would be a sequence, but if we added them up, that becomes a series. So a finite series has a specific number of terms, versus an infinite series goes on. We will talk about how do you find a sum of an infinite series, because it's not always infinity. Sometimes it is, sometimes it isn't. But I keep talking about this word sum, so we're going to go ahead, we're going to draw a symbol for a summation. It's an uppercase sigma in the Greek alphabet, and we're going to use this to say we're going to add it up. So this is called sigma, and it means summation. So we need to put some info on it. In general, what we'll have right here is our rule or our equation. But then what we want to know is like where to start and where to end, right? So what we'll have are 2 spots. What we'll have is our lower limit and our upper limit. So it's kind of telling us what terms to start on and end on. Starting term, ending term. Later when you get in calculus, you'll have a similar symbol that'll have a similar idea. And let's see if I can draw it. I have a lot of practice. It's kind of like a little integral symbol, and you'll have a lower and an upper. But for right now, we'll deal with just this. Our book uses I here. So it tells us the starting term, and then usually they'll put an N up here. And we'll look at some examples. Again, this is kind of our starting term and our ending term. All right, so this one's a lot of things going on here. First thing I'm going to figure out, well, the equation to this. So let's look. Looks like we're just adding 25 each time, and we're starting on 25. All right, so this is kind of like a linear sequence, right? Or series in this case. So we're going to go ahead and call this, if I'm starting on 25, we're going to call it 25n. All right, so that means on term 1 I'd get 25, and each time I'd keep adding. Now, I used n here. Our book often likes to use the letter I, so I'm going to go ahead and change that to an I. There's no real rhyme or reason. And we're going to go ahead and say I equals 1. Well, I can kind of do the math in my head here, because on top I need to say, well, what term am I ending on? Well, how would I get this? If I say, well, when will I get 250? When I equals 10. So I want to put 10 up here to say I'm starting on the first term, and I'm going up to the 10th term in this series. All right, let's look at this one. This one goes on forever. I'm going to go ahead and, I can start with this if I want. Goes on forever, that's nice. And since we're writing the sequence, I'm just going to go ahead and say I equals 1. So let's see what's happening. I'm going to use my strategy from earlier. I'm going to write an equation for the top, which I'm just going to call n, or I guess, sorry, I just said we would use I. So the top looks like it's I. Let me go ahead and write this here. What's happening on the bottom? The bottom looks like it's going up by 1, but starting on 2, so we're actually going to call this I plus 1. There we go. Again, we could use any variable here. You generally want these two to match, so if whatever variable you use here. So let's go ahead and, like, if I wanted to use n equals 1 here, I would just call it like this. Either way works. Let's break down this. So this is a series, because it's sum. And, I mean, it has a pattern. I don't really quite know what it is. It's a quadratic plus 3. And it's telling us to start on the 4th. That's our 4th term, and end on the 8th. So to find the sum, I'm going to have to do this 4 times. I'm going to say 3 plus 4 squared plus 3 plus 5 squared plus 3 plus 6 squared plus 3 plus 7 squared. Oh, wait, there's still one more. Plus 3 plus 8 squared. All right. Oh, man, okay. We could simplify this however we want, right? I'm going to go ahead, I'm going to add up all my 3s. So I have 1, 2, 3, 4, 5. So that's 15 there. So I'm just going to go ahead, I'm going to simplify this to 15. Again, I should point out, I knew where to stop because of this 8. I only went up to 8, started on 4. All right, and then I'm going to have 16 plus 25. Each time right now I'm just doing these numbers. Plus 36, plus 49, plus 64. So I'm going to add these all up. I'm not going to be a hero. I'm just going to straight up use a calculator, y'all. So let's go 15 plus 16 plus 25 plus 36 plus 49 plus 64. And that gets us 205. In the future, we will have certain shortcuts for arithmetic and geometric sequences. But for right now, you can just go ahead and add them all up. So you have some practice problems on the next page. They follow very similar examples. Nothing too crazy here. Give it your best shot. We'll start it with the class next class. All right.